In the previous video, we looked at how to derive the differential equation model for problem number 1 of our second order systems with step inputs problem solving session worksheet. And we used the node voltage method to determine the differential equation that describes the behavior of the voltage across this capacitor C1. What I would like to do is show you now how we could have used the mesh current method, which is based off Kirchhoff's voltage law, to establish the same equation. If you'll recall, when we did the node voltage method, we identified our nodes and we had to establish node voltage equations for two nodes and then end up coupling those two nodes together so that we could come up with the final differential equation that represents how the voltage across the capacitor changes. And this was the equation that we derived from that process. Now, the other thing that we could have recognized is that all of these elements are in series with each other. And since all of the elements are in series with each other, by definition of series placement of elements, they must share the same current. Okay? So we can use Kirchhoff's voltage law to help us determine or derive this same equation, differential equation, to describe the behavior of the voltage across the capacitor. Now what I'm going to do right here is write on the side that the voltage across the capacitor is the same thing as the output voltage that we're looking for. Okay, now I'm going to use the mesh current method, or Kirchhoff's voltage law. I'm going to write an expression for the potential around this loop. So Kirchhoff's voltage law tells us that the voltage across the resistor plus the potential that's developed across the inductor plus the potential across the capacitor must be equal to the potential that's provided by the supply. Now I'm going to express the voltage across the resistor in terms of the current that's shared by all of the elements. The voltage or the potential that's developed across the resistor is just I times the resistance. The potential across the inductor is related, the current and the voltage are related using the derivative relationship of L di dt. Okay, so the potential across the inductor is proportional to the rate of change of current through the inductor. Now, for this term right here, the voltage across the capacitor, that's what I want to know. I want to get my differential equation in terms of the voltage across the capacitor, which is the same thing as V out. So I'm just going to substitute that in here. And all of that has to be equal to Vn. Okay. Now the next step is to recognize is that the current, again, this all goes back to the fact that the current is shared by all of the elements because they are in series with each other. And now it's my job to try to get this current, relate the current to the voltage across the capacitor, which is the same thing as the output voltage. Luckily, we know a relationship that tells us how the voltage across the capacitor is related to the current through the capacitor. Alright, and we know that that relationship is a derivative relationship. So the current that passes through the capacitor, which in this case is going to be the current that is going through all of the elements, is given by C times the derivative of the voltage across the capacitor with respect to time. Of course, Vc, the voltage across the capacitor, is the same thing as the V out, the voltage of the output voltage that we're looking for. So now I can substitute this in because the current through the capacitor is the same as the current through the inductor and is the same as the current through the resistor, as well as the current that is supplied by the supply here. I can take this relationship and everywhere I see an I, plug that in. Of course, I'm going to have to take the derivative of this term as well to substitute it into this relation. So taking this definition of current and how that current relates to the output voltage, I'm going to plug that in here. So that will give me R times C times the first derivative of the output voltage with respect to time, When I take the derivative of this relationship right here, it'll give me a second derivative of the output voltage with respect to time. All right, so that'll be C times L times the second derivative of V out with respect to time plus V out is equal to V in. And now with a little bit of rearranging here, I wind up with the same second order equation that I did using the node voltage method, which required some substitution and some pretty tricky algebra and calculus. So again, we've come up with our second order differential equation that describes the behavior of the system. Now we know that this is our inertia term, this is our damping term, and since we have no coefficient here, or the coefficient here is 1, we know that the stiffness of the system must be 1. Using our general second order variables, we know that now we can calculate the damping ratio. And the damping ratio is given by C over 2 times the square root of K times M, which in this case is going to be the product of RC divided by 2 times the square root of K, which is 1, times M, which is LC, which gives me R over 2 times the square root of C over L. Okay. So now what I'm going to do is I'm going to come over to my calculator in Excel, and I'm going to calculate those values, the value for the damping ratio. The damping ratio, from what I just calculated, is going to be the resistance, R1 divided by 2, times the square root of the capacitance divided by the inductance. Okay, and in this case I get a damping ratio that is identically equal to 1. And since the damping ratio is identically equal to 1, we know that this system is a critically damped second order system. All right, so now using that information, we can calculate the form of the solution. We know what the form of the solution looks like, and then we're going to have to determine the initial conditions. And we'll look at that in the next video.